Okay, the peak time, that means the moment, the time to reach the first peak. Okay, the time to determine the TP, basically here we can see this is in oscillation. Okay, and the first peak basically is here. So assuming that is from the peak to peak, from the valley to from the bottom to bottom here. So from here you can see that basically TP is, if you like, you can approximate it as the half cycle. Okay, and the more precise way is this. Basically, the TP corresponding to the time when the response has a maximum value. So that means here, if you take the d dt of the response and setting up this equal to 0 when t equal to the first value TP, then from here we can precisely determine the TP. Okay. Basically, here this is the response. When the maximum occurred, then that corresponds is TP. So from here we can do the calculations. So if you remember here we have our C is equal to this value, and that one, do I have? I don't have. Let me, I think in your handout you have probably you can take that handout, and our CP is equal to E minus zeta omega n and 1 minus zeta squared and sine omega n minus zeta squared T plus. Okay, so basically we are given this formula, we are given this description, we can easily take a derivative of that. So by taking this, then after the few steps of the calculation, then we can determine TP will be equal to n times pi omega n and 1 minus zeta squared. And because the TP defined as the first one, the first peak, so that means we set n equal to 1. So therefore, this TP is equal to pi and omega n 1 minus zeta squared. Okay. And actually this one is half, exactly is equal to half of the period. Because from, if you look at this one, this curve, this is exactly half of the period of the oscillations. Okay, because the oscillation has at the frequency exactly equal to this, and period equal to 2 pi divided by that frequency, so T equal to half this. So now we have the TP down, then the second one we want to determine is MP. MP, the name is called the overshoot. Okay, so basically that is the maximum value the response will achieve. And again, 1 is our unit step input. Basically, our goal is to have a response to follow 1 as close as possible, as quick as possible. MP is the overshoot, and MP can be determined is this. From here, basically the MP is the value of the C, is the value of the response at the TP, and minus 1, so that is our MP. If you read this graph and here, then you can see basically that is this amount. That amount basically is the difference between the response of the C at that moment to the one here. Okay. So we simply do the calculation, and the way is this, because we already calculate TP here, you simply plug in the TP to here, T to here, and introduce the T by this value and then do the calculations. Okay, then again, here we have a few steps of the detailed calculation, and the result will be equal to, look at become 3. The maximum value of the response at the TP is equal to 1 plus exponent minus pi zeta divided by zeta squared and minus 1. Okay, so the C value of the C at the TP is equal to this one. Then basically here is exponent minus pi zeta and 1 minus zeta squared. Okay, so this is our MP. And then the third one, we're going to characterize TD. So here, say, if we want to know when the system arrives to the half of the command, then the corresponding time we call the TD, and D is for the delay time. TD is such that we calculate C when time equal to TD and that value equal to 0.5 per our definitions. Okay, so simply we solve for this one. Simply you can see you have this value equal to 0.5. You solve for the corresponding value of the T, and that's called the TD. And this one, basically this is not a closed form solutions. So here we can do the approximation. TD can be approximate equal to 1 plus 0.7 times zeta divided by omega n. Okay, and or a better approximation, this one is from another textbook, 1.1 plus 0.125 zeta plus 0.469 zeta squared and divided by omega n. The both equations are good. They both are the linear fit, not the linear fit, the curve fit to simulated numbers. Okay, so the people come up with the two approximations. I believe this one is from our textbook. This is from another reference book. Okay. So that is the TD, and then the third, the other one we're going to find is TR, and TR is this when the moment the value of the response arriving to 1, so this is called the TR. Okay, so the fourth one is called the TR, and I call the rising time. And here the rising time is defined by this when the value of the response and at the time by definition as to the rising time is value equal to 1. Okay, so that's the definition of the rising time. So from here we can solve for this exactly, and so from here the TR will be equal to pi minus theta cosine zeta divided by omega n 1 minus zeta squared. Okay. And how to solve for this one? Go to read our textbook. There's a few lines of the explanations. Okay, so that is for this. And this is the cosine of zeta. Zeta is our damping ratio. So when you punch your calculators, remember have the output in terms of radian. Okay. So if you put in the output into the degrees, then that won't good. That won't be accurate. Then the next one, so right now we have 1, 2, 3, 4, right? And 5. The last one is we call the cycling time. Let me write it down here and label on the graph. Like this. The cycling time is the time for system to reach into within a range. This range can be, so from here to 1 here, that it can be 5% or 2%. Okay. So basically, we're saying the cycling time is the first time for the system response to first enter into the defined range away from 1. And that means the system response basically from there is always refined there, won't be bigger. Okay. So here we have 5% criteria or 2% criteria for determining TS, and depends on the criteria we like. Okay. So I'm going to show you right now in the following is per the 5% criteria. So. We determined is this. We approximate let me use in solid curve for that. So this is exponentially the profile of exponentially decaying profile for the system. Basically, this one is 1 plus. What I'm saying, exponent is this portion here. Okay, we that one is 1 plus. This one should be 1 minus 1 plus. And the bottom one is 1 minus. Okay, so those are the profile. Decay of the magnitude of CT. Okay. So from here we define the TS in this. We have 2 values, and the 2 values basically are basically the same. So here for this moment, and I label that is corresponding to the time, okay? And basically this is the TS, and that means when this component first time to arrive this value, Okay, what is this value here? This value, let me call the criteria is say 5%. Let me say define 5% or 2%. That called the let me give a number called the CTS. Okay, that is the percentage. The criteria percentage is this amount, either 5% or 2%. I'm basically using this parameter. So basically, this value here at that moment is 1 plus CTS, right? Okay. So, and again, for this one, that is the first time when this curve entered into that range. So basically, that is corresponding when the value of this curve is equal to 1 minus CTS. Okay, so from here you can see from either by equation A or by equation B, we can see from, let me say equation A or equation B. Either way, we can always see the CTS equal to this number minus zeta omega n t and this one. Okay, both equations will give the same result if you look at this, both sides carefully. Okay, so CTS equal to 5% or 2% or whatever the percentage criteria you define. Okay, so most of the time, most common criteria is 5% or 2%. Okay, and in our textbook, the numbers are based upon 5%. That is the one in our textbook. Okay, so from here we plug in. Anyhow, let me implement this one. So in particular, this is the moment we define when t equal to ts, and again this one when we write t equal to ts. So basically here, here I introduce the t equal to ts. So basically, if you like, you can simply replace this one as a ts here. That is the one we're looking for. Okay. So by solving these equations, and you can see the ts equal to minus 1 omega n zeta times CTS times 1 minus zeta squared. Okay, so you know if we have all the parameters, that's the system, and if you can define your criteria, say for example 5%, then you have your TS. If you can define CTS, say 2%, or simply plug in 0.02, then you can determine your TS. Okay. Yes.
With the delay time, number 3?
Delay time, you can pick either one.
You don't care?
Yeah, in terms of the test, in terms of the homework, either one. So as long as you tell me which one you pick. And this one, I believe this one is with our textbook. So why not let us unify? How about this? We take this one. We simply standardize our practice. Okay. And here I want to show you something here. Okay. So now in the 2 slides, I'm continue on the discussion of the settlement time. And so this graph is what we seen before, okay? And we have a formula. That formula basically is an exact description of the settling time, and you can calculate. And for that formula, however, that is pertaining to this case. This case that basically has couple peaks, okay. And this graph is oversimplified real situations. For the practical things, basically the oscillation will take a few before entering into the range. Okay, I don't want to misguide you, but for illustration, we're simply using a simplified graph. And the box formula is for this case, okay? And on the other side, if the system has a damping ratio too big, then that has a different scenario like this. For system damping ratio big enough, it only has only one peak, and basically now pretty much come down as the constant. And for this case, the calculation will be different, because this one basically you can see we have to go back to pertaining to these original equations and to fit into this scenario for determining the 0.05 and 1.05, 0.95 this kind of criteria. Okay. So here is the two different cases. And again, in your lecture notes, I put out a whiteboard is belonging to the previous case. For this case, we can, of course, do the calculation similar way. And here for this slide, this one available on whiteboard, basically we tabulate all the possible numbers. The actual numbers, so for the previous system, which is slightly, the system has very slight damping ratio, like this case, we're oscillating a couple of times, okay? And so for this case, basically the actual value corresponding to is here, okay? And in this table, remember that is representing the table, the numbers in terms of omega n times t is basically scale the result by omega n, okay? And the people found, here I want to give you the most, the useful result. And the people try to curve fit to the real numbers. They found this one is the best fit. The best fit, that means the omega n ts equal to this value. Okay, so that is this formula here. Omega n ts equal to this one. So basically omega n divided by here equal to this. This formula is the best curve fitted result to our true value. That is the one we boxed there. And this value only valid for slight system with slight damping ratio. And how slight that would be when damping ratio is less than 0.69. When the damping ratio, the system has too large damping, then basically we use 0.69 as the boundary to divide the two cases. For this system, like this, the feature like this, the basic damping ratio is greater than this. Okay, and for that case, simply the people again calculate exact numbers and then try to curve fit, and then they found this is the best result here. Okay, so basically in everything in short, you can say that sampling time, the settling time have two cases. You simply write it down this result on your lecture notes. Okay, two cases when damping ratio less than this, that is this formula. When damping ratio is greater than 0.69, then that is this. Okay, so that is the quickest result for the summaries for this one. So by talking about the settling time, then basically we have 5 indices we can use to identify the second order dynamic systems. Or on the other side, we can use any of the indices to design the system dynamics we like. So here we can look at a few examples here. Ready? And I'm going to turn off the slides and work on the whiteboard. So Scott probably can take a break. We'll have an example.